and I know this is a little bit of a review, but it's okay. So dy over dx is equal to some function of x and y. This is the example that we have here, just so that you have one. And we're gonna solve this, and don't worry, you don't have to copy this down. I just typed it in so that we'd have it to look at, and then I can copy it up and down. But so here you have a derivative. So we're all familiar with calculus. Even if you're not familiar with differential equations, it's okay. So you have a derivative that's equal to this stuff. So if you want to know the slope at any point, for example, at the point when x equals 1 and y equals 0.5, you can plug x equals 1, y equals 0.5 into this, and you'll get that the slope is equal to 0.25 minus 0.5, which is negative 0.25. So the slope is down slightly at that point. Oh, I need to turn that off. It doesn't bother me. Speaking of my mother-in-law, she's texting me. How did she get my number? Okay, so anyway, so there's that differential equation. We have a starting point. That's all you really need to care about. Oh, and we have a goal. We want to know what's going to happen in the future. So this is today. We want to know what's happening tomorrow. Differential equations are the way that the weather is predicted. It's the way that these bigwigs on Wall Street predict future, like what's going on in the future and so forth. By the way, I had a bunch of friends in grad school, some of whom went to Wall Street and probably created the 2008 financial crisis. But anyway, they were hiring and they were making big money. And I was like, I don't want to do that. I don't want to earn anything. And I guess that's what happened. But anyway, so here's this. And then you don't need to know how this happened, but I came up with the general solution, or no, this is the solution that goes through that point. So this is the solution to this differential equation. Those of you who know differential equations, this one I'd have to use substitution for. So don't worry about it. It's a substitution problem. But anyway, that's the actual solution. So here's the idea. Is we're going to just take little steps, and we'll actually program this. It won't take long. We'll use Taylor's method of order 1 first, which is Euler's method. So Euler's method says that the y of x1 is equal to y0 plus h times f of x0, y0. So all this says is that we're standing here, we're here today at this point, and we're like, okay, what's the slope? And we just figured out the slope is downward a little bit, downward at about 0.25. And we're going to go forward a bit, maybe not an entire step, that's too far. Maybe we'll just go a quarter step and we'll go down a bit, and then we'll reevaluate and say, okay, what's happening now? And then we'll go a little bit more and a little bit more and a little bit more. So that's basically it. And we keep taking little steps until we get to our goal, and then we're done. So that's going to be at least to get us started. As you might guess, I'm going to want to come up with some graphs because it's going to be really cool to see something like this. Here's the actual solution. So this is the truth. And then here's what we end up with when we might have something like this. And you'll be able to see how far off you are from the truth. Whatever, I don't know if that's accurate, but we'll pretend. So the truth is one thing, and then you get, here's what we end up with because we're approximating. And we're hoping that the difference between where we are and the truth is not too far off, because then we can say, hey, tomorrow we're going to have a hurricane. And then the hurricane comes. It'd be embarrassing if we said tomorrow's going to be a hurricane and it's beautiful out tomorrow. Nothing, beautiful sunshine. Okay, so let's go ahead and do this. So give me a sec here. I've got all my notes there. Now I can see everything. Very nice. So if you follow along, you're going to be okay. So here's my goal. Is just so you know where I'm going with this. Is I want to do Euler's method, which is the one that I have written here. Hold on a sec. Here, I know this is a little bit tedious to have me write all this stuff. Okay, so this one is called, it's Euler, and it's a Taylor method of order 1. Okay, so we'll get that one down super easy. And then after we do that one, we're going to do the Taylor method of order 2. And the Taylor method of order 2, give me a sec here. Just copy this, paste it here. So we'll get started on the Taylor method of order 2, and we might finish it. And then you'll do the Taylor method of order 3. But once we do the Taylor method of order 2, here's Taylor method of order 2. Oh, why do I have an extra parenthesis? There we go. Okay, so there's Taylor method of order 2. And then, of course, order 3 is just going to be another plus h cubed over 3 factorial. This is actually a 2 factorial, so it's h cubed over 6. And then the second derivative. So you figured this out on your homework that you had to compute these derivatives. And you'll see what I do to get this one. Once you see how we do this one, you'll understand how you could do an order 3. So we'll do order 2, at least get it started, but order 1 is pretty simple. So let's do order 1 first. Let me pull my mouse over just for a sec. There, now I can see what's going on. Okay, so back to this. So of course, to start off, we're gonna import all of the math. And then also I wanna define this, okay, whatever. I wanna define this, okay, that stuff. So I'm going to call that, so define f of xy. And then I'm just going to define, you can see it up there, it's x times y squared minus y over x. Oh, I forgot, I should return that, shouldn't I? Let's just type return. Or, I don't know. It seems like I feel like I've done this different ways in the past. Whatever. Okay, I'm going to do one other thing, even though we don't really need this yet, and that is I'm going to define f prime. So why am I going to do this? It's because of this. You see down at the bottom, when we get to the order 2, the Taylor order 2, we're going to need f prime. It's right there. So let's define f prime. This is relatively easy. You already know how to do this. Let's go ahead and do our derivative. We're using the product rule. So you have y squared, that's the derivative of x is 1 times, leave the y squared alone, plus 2 times x times y prime, but y prime is f of xy. So now you see how I'm going to be doing this. Now I'm going to do the product rule again. So this is the product rule. Is this big enough? Hold on a minute. Make it bigger. Good enough. There we go. Okay, so hopefully that you recognize this as the product rule for this xy squared. Using implicit differentiation, do the derivative of x first, then you leave the y squared alone, then you leave the x alone, and you do the derivative of y squared, 2y, times y prime. Y prime happens to be that. So you can kind of see where you're going to get f double prime. You can define that one on your own for what we do and hand in on Friday. Okay, so there's f. Oh, I'm not done. I'm going to use the product rule again. I know you might be looking at that saying, how is that the product rule? Well, here's how it is I will do it like this. So the derivative of 1 over x is is 1 over x squared negative. So here this I've done. I left the y alone, and I did the derivative of negative 1 over x, and I got positive 1 over x squared. Now I'm going to leave the 1 over x alone, and I'll do the derivative of y. Derivative of y is y prime. Y prime is, using the differential equation, f of xy. So f of xy over x. There it is. So I believe that's correct for the sorry. xy. I got a little ahead of myself here, and I'm returning this. There. Now it looks better. Okay. So that here, so take a minute. If it doesn't make sense, I can do it on the iPad and write it out if that will make you feel better. But otherwise, you can just be like, oh, yeah, that is. Okay, great. One other option, I was tempted, but I didn't do it, but I was tempted to use SymPy because SymPy could symbolically do the derivative. But I was a little scared, though, of the fact that I'm doing the derivative of a function of two variables, and it was an implicit differentiation problem, and so I was scared that it might not do it correctly. So I thought, let's just do it. So basically, you have to compute that whenever you do a differential, whenever you do this. Okay, so now I can just, I guess, you know what? We should probably test these. Let's just test them. So let's see, print f of, when x is 1, y is 0.5. Yeah, let's do that. And then we will print f prime of 1 is 0.5, just to make sure that we all have the same thing. Let's see, is it working? Oh, it's okay. It's going to take a minute. It always takes a minute to connect and set up your instance. Okay, there it is. So I've got, look at that. That's exactly what I said the slope was going to be, negative 0.5 or 2.5. And then 0.75, that's the second derivative. Is that right? F double prime? Or it's, yeah, it's the second derivative. F prime is, because F is the first derivative. F double prime is concavity. All right. So that looks good. Let's go ahead and start a new thing here. Okay, so here's where I'll put my thing. Now, I'm tempted to call this one of two things. I think I'll call it Taylor method of order 1. So we could define Taylor 1, and then the input will be f, x, y. I'm sorry, I blew it. x0, y0, h, and x1. So let us type in some, well, here, I will do this. Just, you don't have to, well, I don't know. So this is Euler's method. Method, if I can spell correctly, method for solving the diff EQ. I'm going to take 2 lines. Y prime is equal to f of xy, where y of x0 is equal to y0. We are approximating. Look at that. I'm going to go on a 3rd line. This is more commentary than I've had all semester. Okay, so this is, we are approximating y of x1, taking steps of size h. Okay, so just so that we have everything down. So you can guess that when, well, you'll see this, when we get to Taylor 2, the second order Taylor, it's basically going to have almost the same input, very similar. There's going to be a minor modification, but once you get the first Taylor, the Euler's method, so Taylor 1, the rest of it is going to be pretty straightforward. Okay, so probably multiple ways to do this. So just want to warn you, this is just the way I thought of. You probably will be able to come up with a more efficient way, but this way works. So whatever you want to do is fine with me. But here we'll just do this. Start with I equals 0. That's my counter. And then I'm going to do this, x0. I'll explain in just a minute. So this may be why I have to do it the way I'm doing it, is because my goal was that I wanted, here's what I wanted to do. Let's see, let's look at this picture again. There we go. My goal is this. I want to be able to come up with a graph, because it's kind of fun to see a picture of what's happening. I want to be able to see a graph of my approximate solution, all the steps, and superimposed on that, I want the true solution. So, just so I can compare, when we know what the solution is, then we'll be able to see, oh, it's this close. And then, of course, there are going to be differential equations that we can't solve. And then we'll be able to say, well, I think we're probably going to be about this close. Actually, there's a way to find out how close we're going to be, but we'll do that maybe on Wednesday. Okay, so So anyway, that's what this is. I'm just setting up my vectors for the x variables and the y values, x values and y values. Okay, so we've got that. Now, let's see, while. So once again, there's probably other ways to do this. While x0 is plus I times h is less than x1. It's a little inefficient once again. What I should say is not that it's inefficient. Oh, here, I'll just put a colon here. What bothers me about what I did here is, let's say that, well, okay, I'll explain what bothers me in a bit. Yeah, this bothers me, but it doesn't bother me enough to change anything. So there you go. I'll explain what bothers me in a minute. Okay, so we're gonna compute the slope. So m is the slope, right? And this is going to be f of x I, comma y I. So basically, we're just computing the slope. So I suppose I could call this is the slope. If it makes you feel better, you can name it for what it is. And then after this, I'm going to increment my I. So you could either do that, or you could say I equals I plus 1. I don't care how you do it, but either way, now, so I started out at 0, and then right here, it goes up to 1. And then what we're going to do is we're just going to basically take this list of x values, and we're going to grow it. And the same thing with the list of y values. It's not entirely necessary, except that I want to be able to make a picture that looks like this. So that's the only reason. So that's why I say it's probably there's a more efficient way to do this, but I want all of the data. And so that's why I'm going to do it this way. So we have x dot append, and we're appending this with x0 plus I times h. So this is basically just the next x value. So we're starting with x0, and then we have x0 plus h. H is the little step size that we're doing, little baby steps as we go across. And then we have y dot append, and we're going to append this with y of I minus 1. I'll explain why it's minus 1 in just a sec. You probably already have figured it out. Plus h times m. Okay, so that should do it. Okay, so let me just explain why, if you haven't figured it out. It has to do with the fact that back here, so just think about what my I value is. I starts at 0, and then I'm like, okay, you've got this. And then you're like, okay, well, this is true. We're going to do all of this. And so we compute the slope using with I equals 0, x0, y0. And then suddenly I turns into 1. And you're like, well, now I is no longer 0. But when I compute my next y value, I want to use y0 to compute the y value. So that's why I had to say, okay, I got to go back because I've already incremented this. So, you know, you've got to, I could have incremented this down here. There's, yeah, it's just, wherever it is, there's going to be something weird that happens. Like if I increment down here, then I have to, I guess I could have maybe rearranged things. Well, whatever, it's done now. Yeah, I just realized I could have. Yeah, let's do it. Sorry, I just realized I can't let this go now that I see. Let's do it this way. So if we do the y append first, there, that feels better to me. There, now, okay, now it looks better. You can either leave it the way I had it, or if we put the y first, then you're like, okay, the next y value is the old y value plus h times the slope. And then we're like, okay, I gets incremented up, and then the next x value is the original x plus however many, whatever I is, times the h. So how many steps? Okay, yeah, that works. It's different. Okay, almost done. Well, actually, we are done. So now we're going to return x and y, and that's it. So let's see. So let's go back a notch. So just to be aware of the fact that this stuff is all indented once, and then this is indented twice. So there are 4 spaces. I guess an indent is 2 spaces. Okay, so let's test this, and then I'll come around and see if I need to help you. So I'm going to just test this. Let's print, or I guess I could just do this. Taylor 1, was it? Taylor 1, and then we have our F, if we've already defined the F, and then 1 and 0.5 and 0.1, 2.5. Sorry about that. I was waffling because I see. I tested it several times earlier, my other version of this. Okay, so this is what you should have typed in, and make sure that I'm just going to double check that I've actually pressed play with this one because I need those things defined. Okay, now that this should work, let's find out. And if it works, something should actually happen. Oh, there it is. So what should come out is you should have your X values and then your Y values. So those are the Y values, there's the X values, and there it is. Oh, not too bad. Oh, so yeah, so here, by the way, this is the predicted, right there is the predicted Y value. Now that we've seen, now I'll pause, make sure that we're all good. No one's got any problems. You've got a problem? Error, some error. Okay, it's probably an indent or a colon. Let me take a peek, see if we can find your error. Let's see, it says return, and it says numerical result out of, quote, range. Mm-hmm. It looks good. And then this thing doesn't like you. M is F. X, I is 0. That's weird. Huh. Why does it do that? Oh, did you not? Wait, is it up here?
It is up there.
Oh, it's up there.
Here.
No, it's fine. It's fine.
Well,
you can do it for fun. No, I don't think. Why is this different? Let me go. I'll pull mine back up to where it should, because it looks like you've got identical to what I've got. Zoom out just a bit. Because you started with I equals 0. In your X's. This is weird. Let me put in a print statement. Yeah, isn't this fun? I know you guys love yeah, if it was only a little bit more descriptive in the way it spits out errors. Okay, so while this is true, wait, what's that 1 there? 1 times H? Oh, I times H. That's the problem. I'll bet that'll do it. There you go. Nice. Yeah, that was not even the line that it was having a problem with. What in the world? Whew. Well, there it is. Okay. Anyone else have any minor issues? Hopefully as minor as Zane's. Okay, so we've got this. Now, we're going to come, eventually, like I said, eventually I'd like to come up with a graph. But at least for now, while we're testing this stuff, let's not have it spit out the entire list because I've got a step size of 0.25, which is actually pretty big. It would be like me doing this, 1, 2, 3, 4. And I want to do little tiny steps. But if I do little tiny steps, my list is going to be huge. So I'm going to go back here. And instead of returning everything, which would be useful if I was going to graph this stuff, I'm not going to graph it. So at least not yet. We'll do it maybe later. But I just want to see the final Y value. So if you do that, then that's the final Y value. And you don't end up with all of the other stuff. For example, if I do a step size of 0.1, whoops, darn it, then I would have 10 values I'd have to look at, and I don't want to. And then here's 0.01. And, oh, by the way, I should have mentioned that the true solution, so let's go back up here. I've got it typed in, don't I? Up here. Yeah, there it is. So this is the analytic solution. We'll use this eventually. The analytic solution is this. And so if you think about it, when you plug in, we're approximating y of 2, you'll get 1 over 3 times 2, 6, minus 2 squared, which is 4. So 1 over 6 minus 4, that's 1/2. So the true solution is 1/2. And I know it seems silly to actually go through all this trouble when we know what the true solution is, but once again, we're doing this so that we can understand how it works for when we don't know the true solution. Then it'll be super helpful to be able to use this. So true solution is 1/2. So you'll notice that if I have a step size of 0.25, you end up with, I mean, it's pretty far from the true solution. I have to make the step size pretty small. So I'm taking little baby steps, whoops, to get it. So that's like 2 digits of accuracy, maybe almost 3. So that's within 0.004. Let's see if I can get it a little bit closer. What if I do 0.0005? Yeah, I mean, it's getting closer to the truth. Okay, 2.5. Ooh, you're not? Okay, well, wait, let's go back and let's use 0.1. So make sure that your input is the same as mine. And then that's what you should get is 0.46. Okay, that's not right. Let me see why. Well, you got it wrong too? Okay, I'll come back.
When I had the return x, y, it wasn't matching either. The first 2 numbers did, but then the last 3 it listed.
And this is right.
Oh wait. Would be because the y at the end needs to be.
Oh,
above.
yeah, it has to be above.
That'd be it.
Yeah, switch those two. Yeah, switch them. Y pinned. Anyone else need some? Yeah, so you're getting the one before it. So yeah, switch, yeah. I'll wait for a minute. What are you doing? Everyone else have the right numbers? Let me see. Let's see what you got. 0.503.
No clue at all.
Let's see. Okay, we got the slope. Do you have the same function? Wait, why did you put y1 there?
Wait, I thought this one.
Oh, it's an I.
Oh wait, yeah.
Maybe I should use K instead of I. Oh.
I had like 1 plus I or something.
Oh, I plus 1. Oh, because I'd switched things up. Yeah, that's my fault. I kept switching things. All right, are we all, I guess, anyone else? Which one? The first one, just a minute. Let me see if I can find the first one. This up here? Yeah, so all you really need to make sure you have is this function and your importing math. It's those two. But you can test that to make sure that it's correct by doing the thing at the bottom, printing the function at those 2 points. So, does that look all right? Anything else? Other concerns or complaints? All right. Okay. So that's fun. Well, to me, I don't know about to you. Well, I don't know. You don't know what you're looking at, but maybe. But to me, this is disappointing that it takes so many. I mean, think about what this means. I had to take 100 steps. So if you change the step size, that's what this is. If you change the step size to 0.01, going from 1 to 2 is 100 steps. I have to do 100 steps to get this close. And if I do 1,000 steps, it doesn't get that much closer. It's actually surprisingly like not good. I don't know. It bothers me that, okay, so that's 1,000 steps, and I'm only out to, let's see, like basically the 4th digit. I know it still looks pretty good, but still I'm taking 1,000 steps. That's 1,000 calculations. That's a ton of work if you think about it. If you had to do that by hand, imagine doing that like you did this on your homework by hand for some of these problems. It'd be a pain. So that's where Taylor's method of order 2 comes in, and 3. You'll do 3. I'm going to do 2. So here's how I'm going to do 2. Well, let me make sure that everyone's still happy with this one. Because if you're not happy with this, you're definitely not going to be happy with order 2. So now it's time to yell out and pause. And Matthew, are you happy over there? You are happy? It's all I can ask for. Wait, you're not happy? Okay. I don't know. Oh, I had a game I was going to bring. That would have made you even more happy. Well, next time it's just a game that someone gave me that I never took out of the package. I thought you would enjoy taking it out of the package. Okay, well, let's do this then. So anyway, what I'm going to do, so you can do this one of 2 ways. Either do it the way I'm going to do it. You know what? I'll do it this way. You can either copy the entire cell like this, and then I can paste this into this or a different notebook, or you can just copy like this. I guess that's what I'm going to do. I'm just going to copy everything and shove it down here into a new. So notice now I've got that cell that has Taylor 1 and this one that has Taylor 1. So now we've got it twice. So if you've got Taylor 1 working, we're going to make some modifications just a little bit. Now, can I highlight? Hold on a sec. I just realized. If I do this, yeah, bear with me for a sec. I should have thought of this. Edit tools. Okay, here I'll make little notations. Here's what I'll do. So Taylor 2. So I'm changing it to Taylor 2, and the input is going to be f and f prime because we need the derivative. So let me make a notation. So here is the 2 and f prime were added. Okay, just so you know, you don't have to add that yourself. I just wanted to make sure that if you did the copying, I wish I could highlight. You know, like if I could highlight, I would highlight this, but I don't think I can. Let's see, is there a edit? No. Yeah, I think I can't highlight it or change the color. That's fine. So that's what's changing. And then we're going to change this. I'll change this text. This is fine. So this is Euler's. It's no longer Euler's method. It's Taylor's method of order 2 for solving. The rest of this is basically the same. So, in other words, most of this is going to be the same. Here's where things get a little different. Is I have to compute the f prime value. And I will make a note of this. So this is the slope. What is, I guess, acceleration, second derivative. This is new. Okay, so I'll just do this there. So that's new up at the top. So here's all that's changed so far. Whoa, that's not the right screen. Here we go. So all that's changed so far is right up here, what I just highlighted. So I copied the Taylor 1, and I just changed this. I added a little bit to my my description. and then I added this right here. So I'm calling it M2 because I didn't know what else to call it, but I mean, this will do it. Okay, now what we need to do is we need to get this M2, that's the second derivative, or the acceleration, if you will. Let's get it put in here correctly. So let's see, where does that thing go? Okay, there's Euler's method at the top. And here, down here, is Taylor order 2. Taylor order 2. So notice that Taylor order 2 is the same as Euler's method, except it has this additional term. So we're going to have to put this in there, but it's not hard. So it's going to be F prime. Let me go back here. Here we go. Hold on a minute. Okay, there it is. Okay, so then we're going to add to this h squared times m2, that's that f prime, or f double prime rather, or whatever it is. F prime, is it? Whatever. All divided by 2. So all of this here, I'll put this in copy. Here it is. New stuff. There. That stuff. That's the new stuff. That's all I added. I'm pretty sure that the rest of this is fine the way it is. I think that's all I have to change. So just so you know, if you get your Taylor 1 working, and then you take this, copy it, change it to Taylor 2, and fix this, and then put in this line, and then just change this. Then you'll be all done. That's it. Because that's it. It's just this one formula. That's the only difference between the Taylor method. So here's the trick, is when you get to Taylor 3, which is the one you're doing on your own, you're just going to do the same thing. You're going to add in another line here for f prime prime, f double prime, whatever you want to call it. And then you're going to add in another m. It'll be like m3 if you want to call it that. And then you're going to add a little bit to this. And that's it. Let's go make sure this works. Let's go down here. Where am I? Okay, here we are. So I need to change this as well, just so you know. F prime. There we go. Here, I'll do this. Changes. There we go. And let's just go back and do this with 0.25 there and see what happens. So let's see if this works. Oh, that's so beautiful. It does. Here, before we go on, I know I should have thought of this before. I did this earlier when I was working out what we're doing today, but I didn't think of it. So here it is. So what I'll do is I'll do this. So this is print. Let's see if I put this in quotes. Taylor 1, colon, comma. I think that'll do that. Whoa, come on. Let's see if this works. Oh no, why? I capitalized my print statement. Okay, that's better. Okay, so I'm just to label these so that I know what, here, and then we'll do the same thing here. There's this, put this over here, there. There we go. So now you can compare. Ooh, you know what I need to do is I need to change this to be the same thing. 2.5. Ooh, and I got to explain my concerns about this method. We'll do that in a minute. Okay, so maybe I'll do this. I'll right here I could say h is equal to 0.25, and then just put an h in here. See, I guess the reason I'm doing this is so I can compare. Eventually I'm going to graph, or I'd like to graph these, but now I can compare. So we can change this to 0.1. Remember that the truth, the target, the truth is 0.5. So let's see who's going to win. I think you know who's going to win. but this is with a step size of 0.25, so it's a pretty big step. I'm pretty far off. I'm, let's see, 0.09, which is roughly 18% from the truth, whereas this is 0.06. No, 0.006, sorry, which is 1.2% from the truth. So this one's 18% away from the truth. This is just 1.2% away from the truth. So it's already beating it pretty badly. Now, if I do a step size of 0.1, check it out. I'm still 8% away from the truth here, whereas this is 0.12% away from the truth. So this is getting really close to the truth. And then if I do a step size of 0.01, that Taylor method of order 2, now this is 100 steps, but bear in mind this was 10 steps. 10 steps! Look how close we are. Now 100 steps, look at that. It seems like every time we increase by a factor of 10, we're getting another 2 digits here, whereas this is just still floundering at the second digit. So, so Taylor, oh, that should say Taylor 2, sorry. The Taylor 2, we change this to Taylor 2. There we go. There we go, yeah. So, so the Taylor method of order 2 is better than Taylor method of order 1. I suspect that you'll guess that Taylor method of order 3 is better than order 2, but how much better? That's the question. And so that's something that we'll have to deal with in the future. So let's do one more thing before we go. Let's see if I can get the graphing to work. So give me a sec here. I'm going to grab because we've done graphing before. Hold on a sec. Oh, is there anyone having trouble with any of these? Your numbers working out? I can go back or I can help you out. Let me see if I can find my graphing stuff. Here, just a sec. Taylor methods, adaptive integration. It was adaptive integration? Is that where we did the graphing? I think it is. Just a minute. Oh, no, I don't have the graphing there. Huh. Were we supposed to do graphing? It's weird. I've got, looks like I did some graphing. I didn't do as much as I thought I would. Well, that's all right. Well, we can do some graphing here. Let's see if I can remember how to do graphing just by, from my memory. This thing caps lock is on. Okay, so let's do this. So import matplotlib dot pyplot. Is that right? As plt. I think that'll do it. And then import. And I've been trying to avoid NumPy, but here we go. So, so just so you know what these are, so this is a plotting package, and then this thing is the NumPy. It has a lot of, it does a good job with vectors and dealing with functions of vectors. So you can actually do a function, evaluate a function at a vector and stuff like that. So that's what that is. I'm not sure that I'm going to need that. Like I said, I'm just going from memory. I didn't check ahead of time, but I know this is something that I want to do. So let's see if we can do it. So let's do this. How about x true is going to equal linspace. I'll explain in just a sec what this means. Oh, sorry, in P. Sorry, in P dot linspace. So this is just going to create a vector, and I hope I can remember it's going to go from 1 to 2, and it's going to have a step size. Oh, look, it's got a little hint there. Start, stop. Let's see if this works. Let me just make sure it works. X true. Oh, it doesn't like me. What doesn't it like? np.linspace. Start, stop, endpoint, what? Float object cannot be in, oh, okay, sorry, now I remember. So I need to make this 1000. Okay, that's better, yeah. Okay, so what that's doing is, oh, weird. Oh, this reminds me, my complaint, okay, interesting. I need to make this 1001. Wow, okay, yeah, that's much better. Yeah, left out a bunch of them. But yeah, okay, let's just back up just for a sec. I want to complain about my code. So what's wrong with my code? Well, here's what's wrong with my code is if I go back here, let's just go up to Taylor 1 just briefly. We'll come back to the graphing in a minute. If we don't get the graphing done today, which we probably won't, we'll do it next time. Okay, so here, if we do this, 0.1, and I'm going to go up here and just change my code briefly to return both X and Y, just so that we can see this. So, oh, interesting. Wow, there's some round off error in the middle there. But if you do, if your step size is 0.1, then you're going to end up getting to 2. So if the step size is 0.1, you get to 2, and that's all well and good. Let's say the step size is 0.25. Everything is going to operate the way you would expect, 0.25. So there you go. We have that. We're all happy. What if I make my step size 0.3? Where is this going to end up? It's not going to end up at 2, is it? So that's why my code is terrible. Well, it's not terrible. It's just, whoops. There it is. So it ends at 2.2 because, remember, it ends once you get above 2. So it's like 1, 1.3, 1.6, 1.9, whoops, 2.2. So unless you are clever and choose a step size that is, divides the space evenly, you're going to overshoot. So probably a safer, it's too late now, just be aware of this when you're using this, but probably a better way to do this, this is just the way that I ended up doing it. And if it bothers you as much as it's, I'm tempted to fix it, but I'm not going to do this to you right now because this does work. Just be aware that you need to have your step size be sort of divide your space evenly or the interval evenly. But one way to fix this is instead of using H, you could use in and say we're going to do in steps and then compute H down here. That's probably much safer because then you have your in, that's the number of steps. And then down here you'd say, okay, H is going to be x1 minus x0 divided by n. In fact, oh, what an easy fix. Okay, I'm going to do it. I know, I just said that I wouldn't, but it's just so much better. So we have in now, and then right here, we'll do H is equal to x1 minus x0 over n. Already I'm seeing other problems. I mean, what if someone chooses x1 to be smaller than x0? I don't know, I can't fix that. Well, it might still work if you did that. Well, no, it wouldn't. Yeah, because of this. Well, no. What I'm saying is if someone was dumb, I'm just saying if you had someone do that, you would want to have like an error message, I guess. Yeah, so you can't, I guess that's something that if you had commercial software, if we were making people pay for this, we'd want to fix. Okay, so now if you do this, I like this so much better. If you do this, you're gonna have to change everything down here because instead of having 0.3, you would put 3 because I'm doing 3 steps, and then check it out. Look at that, there's my steps, nice even steps. So 1 1/3, 1 2/3, and then you get to 2. Yeah, I like this way better. So then I can do 10 steps. Whoops, that's 103 steps. Oops, there it is. So there's my 10 steps. I don't know what's going on with this. some sort of, well, it's just because of the, you computer scientists, you're like, yeah, that's typical, right? Like, it's like, whatever. It's because the machine, the representation, the way machines represent numbers is different, and it's all base 2. So there's something going on there with the rounding. But whatever. So if I wanted to do 4 steps, let me just do one more, and then, yeah, I like this better. Don't get confused, though. Either stick with the way that we set it up or change everything. And by change everything, I mean just those 2 lines. But if you try to mix the 2, you're going to have problems. And we're going to be spending a lot of time on Wednesday debugging. Okay, well, anyway, getting back to what we're doing. Let's see, we'll get it started here. I want to graph this. Okay, so I've got my x, the true values of x, and then what can I just function this? I don't know if I can. Let's find out. So let's see, y true is equal to, wait, where's my function? Didn't I define it up here? Hold on a minute. I didn't. Okay, the actual solution. This is the analytic solution. I'm gonna, here we go. I'll just define it way up here at the front end. So define true solution, x, and oh no, what happened? Sorry, I forgot. Here we go. And I'm gonna return, what is it? 1/3 times x minus x squared. Is that what it was? Yeah. So there's my true solution. So I needed to input that somewhere. You need to have it somewhere. So there it is. I don't care where you put it, but this is so that I can graph this. So let's go down here and let's see if it'll let me. I can't remember if this works. True solution. Uh-oh. I need to capitalize S. Just a sec. If not, I'll just have to make a loop of x true. Will it like me? It liked me? Oh, that's so beautiful. So notice what it did. Let me see. Print x true. Just a minute. And print. This is why one of the benefits of using NumPy. Y true is, yeah, it's just been a while since I've done this. So now, yeah. So basically, it took all of these numbers, there's 1,001 numbers there, and plugged each one individually into my true solution, and I got this. And now I can just plot. So let's see, PLT, is it plt.py plot? It's been a while. Let's try this, x true, comma, y true. Let's see if that does it. Ooh, didn't like it. I'll have to look up exactly. Yeah, maybe. Yeah, that's better. Oh yeah, there it is. Yeah, there it is. There's my, oh, it's so beautiful. Okay, so I guess next time, I've got it all set up. Next time what I'll do is I'll combine that, I'll combine this with the actual, the numerical solution, those points, and you'll be able to see, like actually visually see how far away you are from the truth. And what'll happen is over at the front end, it's going to be pretty close to the truth, but then as you get over towards here, things get further and further away from the truth. So we'll deal with that next time. We also have to deal with errors, like error bounds. That's in your book. So if you really want to, you can take a preview of that in the Tea Time book. But yeah, I'll also hopefully have the actual assignment ready by Wednesday that's due on Friday, which will be the Python. But you're well on your way. If you really want to get a jump on Friday, what you could do is go here and basically just copy the Taylor 2 stuff and make a Taylor 3, which is just going to add an additional, just one more term right here. So there'll be one more term. It'll be h cubed times m3 when you get that, divided by 6, because 3 factorial is 6. All right, so that's it. So I guess there's no real homework for Wednesday. I have homework. I have to get that homework for Friday up. So if you do have any troubles, stick around. Otherwise, have a great day. I'm going to stop the recording in case you want to chat.